All right, so we've been talking about why it is that ATP is such a great place to store some of the free energy that organisms extract from their environment or from the molecules they can acquire in the environment that they break down in order to generate the materials and the energy they need for life, right? This very high hydrolysis-free energy, coupled with the fact that the transition state for hydrolysis of ATP, excuse me, is quite high in energy, makes ATP fundamentally thermodynamically unstable, but kinetically stable, which is a perfect place to park the energy one wants to tap at will and in the right place at the right time, but without it leaking away all by itself very easily, right? So while we're thinking about this idea, it's worth pointing out that another way to talk about the fact that ATP has this high hydrolysis free energy is to also, or to think about it in a slightly different way, or point out the idea that this is equivalent to the idea that ATP has a very high phosphotransfer potential, right? So I've been talking about it from the context of hydrolysis, right? As if water was going to split that bond. But ATP will quite happily donate that phosphate group to all kinds of other nucleophiles for important purposes that have to do with catabolic breakdown or with synthesis, anabolic synthesis of things. And while we're sort of on the subject of high transfer potential, it's probably worth noting that ATP is not the only molecule with a high phosphotransfer potential. And in fact, there are several other molecules that have significantly higher phosphotransfer potentials that are going to be important for the purposes of actually synthesizing ATP, right? So keeping in mind this idea of phosphotransfer or the potential to transfer that phosphate group to another appropriate nucleophile is a really important thing to remember. So, and this scales with the sort of thermodynamic instability of that molecule. So just as a reminder, right, ATP, as we've been talking about, will happily hydrolyze, or now we're thinking about it, transfer that phosphate group with a free energy, standard state free energy of hydrolysis of about 31 kilojoules per mole, right? And like I said, there are other molecules that have even higher phosphotransfer potentials. A really good one, right, is a molecule known as phosphoenolpyruvate, which you guys may remember. If you don't, you're going to see it again soon. Phosphoenolpyruvate looks like this, right? We have, whoops, yeah. And phosphoenolpyruvate will happily release that phosphate group to water or to other things that it's going to react with, right? And the main thing you're going to see it used for is actually taking ADP and synthesizing ATP from it. And you can do that because the hydrolysis free energy, again, that phosphotransfer potential for phosphoenolpyruvate is significantly higher. It's about 2 times higher than that in the standard state for ATP. It's like minus 62 kilojoules per mole, right? Right. Another one, there's another one, an important one that you guys are going to see, all right, is this molecule. Right. This is, of course, 1,3-bisphosphoglycerate. And 1,3-bisphosphoglycerate has a phosphotransfer potential that is also higher than that of ATP. Its standard state free energy, hydrolysis free energy, is about minus 49 kilojoules per mole, right? Okay, so this idea of phosphotransfer potential is going to become really important when we think about how it is we're going to be making ATP from other molecules. And both of these guys, as you'll see, we go along, both phosphoryl pyruvate and 1,3-bisphosphoglycerate are going to be important when we actually do some synthesis of ATP. And they pull this off because their phosphotransfer potentials are even higher than that.